Yes, so let's expand that out. 1 minus theta. I don't need parentheses around that. Then you're going to have what? A minus a 1 plus theta squared minus 2 theta. Now notice what happens here. You got a minus theta. Let's see, we have a, oh, actually, no, that's right. I've got that right. Okay, so what do we have here? We got a 1 minus a 1, so that disappears. We have a minus theta plus 2 theta, and then we have a 1. So this, wait, this is not, one minus theta, then we have a minus, we square this, we get 1 plus theta squared minus 2 theta. So that's right. So what does this simplify to? This term within brackets. 1 minus 1, so that disappears. So minus theta plus 2 theta.
Theta minus theta squared.
Okay. Oh, okay. That's right. Okay. So this is right. So that cancels. We have a minus theta plus 2 theta. So you get a theta, right? Times, wait a second. What's going on here?
Minus theta squared because
Yeah. And then you have a minus. Oh, yeah, that's right. Okay. I had it right. Okay. Okay. That's right. Okay. Now, and let's not forget this term here. Theta times 1 minus theta u squared plus that. Okay. Now we factor out the theta here. And this becomes theta times 1 minus theta. There we go. So finally, the final simplification is this. Theta times 1 minus theta u squared plus theta times 1 minus theta times v squared minus 2 theta 1 minus theta uv. Is that greater than 0? Now notice you could divide through this equation by theta times 1 minus theta. Okay. Because theta is between 0 and 1, so these things will always be positive. So you could divide through both sides by that, and then the equation would just reduce to this: u squared plus v squared minus 2uv. Is that always greater than 0? And the answer is yes, because what does this reduce to? What is u squared plus v squared minus 2uv? It's just u minus v squared. And that must be greater than 0 because u and v are distinct points. So this term right here, u minus v squared, has to be greater than 0 because u and v are different values. Okay. So that proves that this function f of x equals x squared is a strictly convex function. Okay. I chose the simplest example I could, believe it or not. We've been through that once. Okay. So for now on, we'll use the mathematical methods. Okay. So what we've shown is the height of the line segment, which is this, in this case, is always greater than the height of the arc. It's a convex function, strictly convex. In fact, if we graphed it, that would have been pretty obvious, wouldn't it? It would have been intuitively obvious. Yet, we have to be rigorous. So y equals x squared looks like this. You connect any 2 points, the line segment always lies strictly above the arc of the function. Okay, at least for theta between 0 and 1. Okay, if you, at the endpoints, of course, it would be right on the function, but theta is restricted to be between 0 and 1. So these line segments always are above the function. Strictly convex function. Okay. Now, it turns out that there are some mathematical methods we could use to get this same result in a more straightforward manner. So as long as our function is differentiable, we can go ahead and use these mathematical theorems. Okay. If you look on page 324, page 1124, equation 1124. And this is now 324. And again, I'll just read it. It's in the book. But I'll just read what the book says on page 324. Now, we're dealing with a case where f of x, where x is just a single variable. So we're dealing with a case where y is a function of a single variable x, f of x. And 1124 says the following. A differentiable function, f of x, is, let's take the concave part first, is concave if and only if for any given point u and any other point v in the domain, the following is true. And this is the case where f of x is concave. Okay. If and only for any points, two distinct points, u and v, we have the following. F of v is less than or equal to f of u plus f prime of u times v minus u. Okay. And perhaps it would be helpful if I draw a picture first before we get into the math. And I want to thank you. I think this water is helping, Ian.
It's sparkling water.
It's sparkling water. It's just not water. It's sparkling water. Thank you. Not, it's Perrier. Perrier, okay, yes. Thank you. I probably owe you some money for that, Ian. All right. Let's draw a picture here. Here is x. Here is f of x. Now, u and v are just two distinct values of x. So let's draw a function. It's obviously it looks concave. Okay, a function typically have that shape. That would be concave. And let's draw. Oh, let's say this point right here. Let that be u. And what we're going to do is, let's use a red pen now. We're going to draw the tangent line. See, this is f prime of u. So we want to draw in the derivative right there. We want to look at this tangent line. Okay, so that'll give us the slope of that tangent line gives us f prime of u. So what this is saying, if you pick any other point V, could be any other point. In this case, let V be to the right. It could be to the left. That would be okay also. But let's let V be this point right here. And here is f of v. Here's the true value of the function. And what this is saying is the true value of the function f of v is less than f of u plus, if you go along this tangent line, you would get this part right here. The part you're adding to it would, let me draw a dashed line further up. The right-hand side at this value right here would be f of u plus f prime of u times v minus u. Because you see v minus u, that's the run. What is f prime of u? Well, if you're going along this tangent line, that's the rise over the run. So this is the predicted value using the tangent line. So this value right here would be your f of u plus f prime of u times v minus u. Or in simpler words, you could say, if you take the tangent line at any point, that tangent line lies everywhere above the concave function. See this red line? It lies everywhere above the function. If we were to continue this function down, it would look like that. Okay, so the tangent line lies everywhere above the function. That's what this equation right here is saying. Okay. Okay. Now, if f of x is concave, if and only if this holds for all distinct values of u and v. Now, if we alter this slightly and make this a strong inequality, then that's a condition for f of x to be strictly concave. Okay. If I make this a strong inequality, then this is f of x is strictly concave. I'll just put a The condition for convexity is just the opposite. The condition for f of x to be convex is this. If and only if for any 2 points, u and v, this condition holds. Now it would be that the tangent line is everywhere on or below the function. Okay. And for strictly convex, we would just change this to be this. Okay. A strong inequality. Okay. Let's consider the example we just did. Y equals x squared. Or f of x equals x squared. Now, in this case, we want to use this formula right here. We suspect, based on our earlier results, that this function is strictly convex. Okay. So, what is f of u and f of v again? Kelsey, what is f of u? Oh, very good. Very good. You got it. You're over it. Yeah. Same as before. Now, the only thing else, okay, what is f prime of u? Yeah, notice that f prime of x here is what? since f of x is equal to x squared, so f prime of x is equal to 2x. Okay. So f prime of u is equal to 2u. Okay. All right, so let's just substitute in and see if this holds. F of v, that's v squared, isn't it? Is that greater than f of u? F of u is u squared. Plus f prime of u is 2u times v minus u. Okay. Let's bring everything over to the left-hand side. So let's write this as v squared minus u squared minus 2uv. So we have a 2uv here. We bring it over, so it's a minus 2uv. And then notice we also have a minus 2u squared. So when we bring it over, it'll be a plus 2u squared, won't it? Okay. So look what this gives. When we simplify this, we have a minus u2. We get v squared plus u squared minus 2uv. Is that greater than 0? And the answer is yes, because that is obviously just a v minus u quantity squared. And that clearly, since u and v are distinct points, that's clearly got to always be greater than 0. Therefore, this is strictly convex. So that was quicker. That was definitely quicker. Furthermore, we can bring up the importance of this result. Let's go back to the case where we have a concave function. The condition for the function to be concave is this. F of v is less than or equal to f of u plus f prime of u times v minus u. Okay. Suppose we pick the critical point of x. Then the first derivative, and let's say the critical point of x is u, then f prime of u is 0. So let u be the critical point of x. Then f prime of u, by definition, is 0. So this equation reduces to just f of v is always less than or equal to f of u. So what does that mean? That's for all values of u and v. So it means at x equals u, you have a what? You have a max, a global max, because this is saying the value f of u is always greater than or equal to f of v. Therefore, if you know in advance, you know that your function is concave. If you satisfy the first order condition, you have a global maximum there. Not just a local max, but a global maximum. Because you've proven then that f of u is always greater than or equal to f of v. Furthermore, suppose that this condition holds. Suppose that the function is strictly strictly concave. I'm thinking about quasi-concave because I was just dealing with that. But in this case, the function is strictly concave. then you know that f of u is a unique global maximum. Okay, it's strictly greater than f of v. Not greater than or equal, but strictly greater. In this case, you know that you have a unique global maximum occurs right at this value, f of u. Okay, so this is an important result because the first and second order conditions we derived earlier were just guaranteed a local maximum or a local min. Okay. By the way, this same argument holds if you're looking for a global minimum. Only now what you need is for your function to be what? In order to guarantee a global minimum, you would want your function to be what? Strictly convex. Because if you reverse this, if you can show that f of v is always greater than this, then that means you have a strictly convex function. Now, again, you look at your critical point. You want to minimize the value of the function. Look at your critical point. This term drops out. So this reduces to just f of v is always greater than f of u. Therefore, f of u must be your global minimum. Okay. So if you know your function is strictly convex, you satisfy the first order conditions, you don't really have to worry about the second order conditions because you're guaranteed to have a global minimum right there. Okay, so that's an important result. There is a slight extension of this to the case where you have a function f of several variables, x1, x2, xn. Then the version of this equation is slightly different. And this is equation 1124 prime. Prime. And this is actually on page 325, thank you. Now, f of x, let me write it this way. F is a function of n choice variables. This function f of x, 1 x2 xn, is concave if and only if the following condition holds. U and V are now, again, two distinct points. But point U is really U1, comma, U2, comma, UN. It's a point in space. And V is the same thing. So point V would be really V1, comma, V2, Vn.